Welcome, everybody. My name is Filipe Mulonde. I am from Angola. It's a country in the south of Africa. I hold a bachelor degree in software engineering from the St. Petersburg Polytechnic University, and I am currently a master degree student in AI and machine learning at the same university. The foundation of C++ atomics, the knowledge you need to correctly use C++ atomics, is a series of talks. And today I will present the first talk in this series of talks. Anatomy of C++ atomics. This is how I see atomics. I divide them in 4 key components that one needs to know in order to understand atomics. Need to understand atomic as a class in C++, for example, how atomic interacts with the other feature of the language. Need to understand the guarantees that are given by the C++ memory model. Need to understand how atomics interact with compiler optimization, and need to understand how atomics interact with hardware optimization. For the first 15 minutes, I will talk a little bit faster because it's only content to give context to understand the rest of the talk. I would like to acknowledge the work of Onur Mutlu. He is a professor at ETH Zurich, and I used to watch a lot of his lecture in computer architecture. And some of the slides present in my presentation today were taken directly from the slide for his lecture in computer architecture, and some of the slides present in my presentation were inspired by the slides in his lecture on computer architecture. The first talk in this series of talks about atomics will be about hardware. So that's why I will start by making a brief description of computing system. A computing system has 3 key components: computation, communication, and storage and memory. And these 3 key components are used to create different platforms to achieve different goals or metrics. There is no need for atomic operations if there is no parallel computers. So that's why it is important to understand why parallel computers. The original goal was to improve performance, but there is also other goals, that is to reduce power consumption, to improve cost efficiency and scalability, to reduce complexity, and also to improve dependability. There is 2 types of processors. There is loosely coupled mode processors, and there is tightly coupled mode processors. For the rest of this talk, I will be only cover tightly coupled mode processor, where we have a network of cores sharing global memory address space. And the C++ standard does not support programming for loosely coupled mode processors. There is many issues with tightly coupled mode processors, but today I will be only cover memory consistency. Here we have a processor-centric design, and in this processor-centric design, we have a network of cores that are connected by a shared interconnect, and this network of cores are sharing memory. And the question is, why do we need atomics? We need atomic operations for 2 reasons. First is atomicity. With atomicity, we want to ensure that only one core is operating on a particular memory location at a given time, and the other cores cannot see this operation partially done. And we also need synchronization or visibility to ensure that the result of the computation of cores is visible to other cores when needed. Now let's talk about the difference between memory consistency and cache coherence. Consistency is about ordering of all memory operations from different processors, that is, to different memory locations, a global ordering of access to all memory locations. Coherence is about ordering of operations from different processors to the same memory location, a local ordering of access to each cache block. With consistency, we care about the order of operation on all memory locations. With coherence, we care about the ordering of operation in a particular memory location. So that's the difference between the 2. Now let's talk about memory ordering in an MIMD processor. Each processor memory operation are in sequential order with respect to the thread running on that processor. And here we assume the processor obeys the Van Neumann model, and multiprocessor execute memory operation concurrently. The question is, how does the memory see the order of operation from our processor? In other words, what is the ordering of operation across different processors? Now, let's understand why this question is important by using this example. Can two processors be in the critical section at the same time, given that they both obey the Van Neumann model? The answer is yes. The another question is, what the second question has to do with the first question? Well, what the second question has to do with the first question is that these two threads can be in the critical section because these two threads don't agree in the order which the memory operations took place. So now let's understand a little bit what we have here. So here we have two threads, and they have global variables, and these global variables are used to communicate between threads. They are used as flags. And I also like to mention that we have some letters here, like A, B, C, and D, that I just use them to indicate instructions. So when I say instruction A, I mean the variable S1 being set to 1. Now let's understand how this works. When a thread wants to enter the critical section, the thread sets his flag to 1. In this way, the thread is communicating to the other thread that he is in the critical section. After that, the thread checks the flag of the other thread or processor to see if this thread is in the critical section. If the second thread is in the critical section, then this thread, the first thread, should not enter the critical section. And the same thing with the thread number 2. Now let's understand why is it important to protect shared data. Threads are not allowed to update shared data concurrently for correctness purposes. Access to shared data are encapsulated inside critical section or protected via synchronization constructs, locks, semaphore, and condition variables. And only one thread can execute a critical section at a given time. That's the mutual exclusion principle. A multiprocessor should provide the correct execution of synchronization primitives to enable the program to protect shared data. So now let's go into more details why two threads can be at the critical section at the same time, right? Here it was not clear, but now using this example here, we go in a sequential manner why and how these two threads can be at the critical section at the same time. So at time 1, the thread 1 set his flag to 1, but instead of updating the memory directly, this thread is writing in a local buffer. And the thread number 2 does the same thing. At time 2, the thread number 1 checks the flag of the thread number 2 to see if the thread number 2 is in the critical section. But while loading the flag of the thread number 2, it's a cache miss, so you need to send a request to memory. And the same thing happened to the thread number 2 with respect of the flag of the thread number 1. At time 3, the request that the thread number 1 sent to memory arrives, and the value of the flag of the thread number 2 is 0. Why? It is 0 because the thread number 2 wrote to a buffer instead of update the memory directly. Then, and the same thing happens to the thread number 2 with respect to the flag of the thread number 1. Because these two threads read 0, these two threads can enter the critical section. And remember, when we talk about shared data, we saw that two threads cannot be at the critical section at the same time, because if two threads are in the critical section at the same time, they may be operating in the same memory location at the same time. And that's a problem. At time 5, the instruction A finishes, and the thread updates the memory. And the same thing happens with the thread number 2, the instruction say finish. The instruction say is complete, and the S2 is in memory. And the problem is that threads don't agree in the order in which memory operations took place, right? For the thread 1 point of view, the instruction A happens before C. But for the point of view of the thread 2, the instruction C happens before A, right? So both cannot be correct. The problem is that two processors did not see the same order of operations to memory. The happened before relationship between multiple updates to memory was inconsistency between the two processor points of view. As a result, each processor thought the order was not in the critical section. How can we solve this problem? One idea to solve this problem is to use sequential consistency. Here we have a formal definition of sequential consistency, but I will use a more abstracted way to explain sequential consistency. In sequential consistency, memory works as a switch, and when this switch points to a processor or thread, we have the guarantees that all the memory operations performed by this particular thread or processor will be visible to other threads. And because of that, we can create a total order in which all the processors agree in which order the memory operations took place. Here, we have an example of sequential consistency, but I will not go through this because in the talks that I will give in the future, in this series of talks about atomic, I will have a special talk where I will cover the C++ memory model. But it's important to mention that even when we're using sequential consistency memory model, a program still have multiple execution orders, multiple different execution orders, and which order is observed depends on implementation and dynamic latencies. So let's talk about issues with sequential consistency. Well, sequential consistency is a nice abstraction for programming, but have two issues: too conservative ordering requirements and limits the aggressiveness of performance enhancement techniques. Is the total global order requirement too strong? Why? Because the ordering of operation is important when the order affects operations on shared data. That is, when processors need to synchronize to execute a programmed region. Do we need global order across all operations and all processors? It's almost the same question that I made here. So how about a global order only across all stores, like the x86 total store, for example? Or how about enforcing a global order only at the boundary of synchronization? Here, for example, when we have a lock, we only need to guarantee that the operations inside of the critical section do not exit the critical section. But all the operations outside the critical section and the operation inside the critical section, they don't need to be executed in a sequential consistent manner. And because sequential consistency memory model affects performance, scientists and engineers have proposed techniques to speed up sequential consistency memory model. And here we have a proposal at the hardware level. And here also we have a proposal at the compiler or software level. And because sequential consistency, again, affects performance, scientists and engineers have proposed weak consistency memory models, like the acquire and release memory models. And the C++ programming language also provide the memory model acquire and release. Again, we will have a special talk where I will cover the C++ memory model. And the C++ programming language also provides a more weaker memory model, that is the relaxed memory model. And if you want to understand these execution graphs, mathematizing the C++ concurrency is the paper to read. We saw in the previous slides that two threads can be at the critical section at the same time because instead of writing to the main memory directly, these threads were writing to a buffer. This outcome may be surprising to some of us, but this outcome is expected from almost all modern computer architectures. With that, we can conclude that this buffer influenced the memory model of almost all modern computer architectures. The memory model of some architectures were influenced by this buffer and another mechanism inside of the microarchitecture. But the x86 total store memory model were influenced only by this buffer. So the rest of this talk, I will be covering how this buffer, that's also called Reorder Buffer or store queue, within the x86 core influenced the x86 total store memory model. In the previous slides, we also covered a sequential consistency. The TCO memory model is close to sequential consistency. The difference between sequential consistency and TCO is that architectures that support TCO, because of the presence of the buffer, they allow that a store can be reordered with a subsequent load in the program order. Now let's understand a little more about the difference between sequential consistency and TCO. Sequential consistency execution are a proper subset of TCO execution. All sequential consistency execution are TCO execution, while some TCO execution are sequential consistent execution and some are not. Because of that, the TCO memory model is weaker than sequential consistent memory model. Why? Well, the TCO is weaker because all sequential consistent executions are TCO execution, while some TCO execution are not sequential consistent execution. So that's why TCO is weaker. Here we have another example that illustrates the difference between TCO and sequential consistency. Under sequential consistency and TCO, loads and loads cannot be reordered, loads and stores cannot be reordered, stores and stores cannot be reordered, but a store can be reordered with a subsequent load in TCO, while under sequential consistency, it cannot be reordered. So that's the difference of TCO and sequential consistency. Systems that support TCO do not provide ordering between a store and a subsequent in-program order load, although they do require the load to get the immediate value of the early store. In situations in which the programmer wants those instructions to be ordered, the program must explicitly specify that ordering by putting a fence instruction between the store and the subsequent load. As I said, for the rest of this talk, we'll be covering hardware. We are going to understand how the reorder buffer or store queue within x86 cores influenced the x86 TCO memory model. So, when we are studying memory models, why is it important to understand the hardware? One of the reasons of why is it important to understand the hardware is because it is the knowledge that is needed to verify if the compiler is providing an efficient compilation to the hardware. And to illustrate why is it important, I have some question over here. Do we need fences to implement the sequential consistent memory model on x86? The answer is yes, but why? Do we need fences to implement the acquire and release memory model on x86? The answer is no, but why? So we have one question here. Why do the compiler and hardware change the order of execution of instructions? Well, the answer is performance. The other question is, why is it possible to gain performance by changing the order of execution of instructions? Right? Why, by just reordering instructions, we can gain performance? So one can only truly answer this question if one knows the hardware in which he wants to use atomic operations. Why to keep a buffer inside of a core? As I said, almost all modern architectures use it as a buffer. So this buffer has influenced the memory model of almost all modern computer architecture that we have today. One of the reasons of why some architectures uses these buffers is to provide precise exceptions and to help to solve the problem of memory disambiguation on an out-of-order processor. So in an out-of-order machine, in order to provide precise exception and to handle execution of loads and stores out of order, this buffer is needed. And this buffer also helps with performance. And why performance is important? Performance is important because we want to solve the hardest problems in the world. Understanding pipeline will be important for the rest of the talk. So let's start by understanding a pipeline processor. The goal of a pipeline processor is to gain more concurrency, to have a high instruction throughput, because we want more work to be completed in a cycle. And the idea of the pipeline processor is that when an instruction is using some resource in each processing phase, process other instructions on either resources not needed by that instruction. Example, when an instruction is being decoded, fetch the next instruction. When an instruction is being executed, decode another instruction. Here I have an example of a pipeline processor that has 5 stages. So when an instruction is at the write-back stage, we can have another instruction at the memory stage, another instruction at the execute stage, and another instruction at decode stage, and other instruction at the fetch stage. With that, we are solving the problem of idle resources, and we are exploiting instruction level parallelism. So here we have an example that illustrates the performance gain of a pipeline processor. So we have 4 instructions of the same types. It's an add. In a multi-cycle processor, it will take 16 cycles to complete the execution of these instructions. But in a pipeline processor, it only takes 7 cycles. And in a pipeline processor, we have the benefit that when we are in the steady state, the pipeline can produce 1 instruction per cycle. The steady state is the stage where the pipeline is full. The problem is that here we assume an ideal pipeline. But instruction pipelines are not an ideal pipeline. Why? Because we don't have instructions don't have identical operations. It's also called the problem of external fragmentation. Some pipe stages are idle for some instructions. The other problem is uniform suboperations, also called internal fragmentation. Some pipe stages are too fast, but all take the same clock cycle time. The another problem, probably the worst, is that instructions are not independent. So the pipeline stalls because instructions are dependent of each other. The pipeline is not always moving. It's also important to understand data dependencies. There is 3 types of data dependencies. There is flow dependency, that's a read after a write. Here, the first instruction is writing to register number 3, and the second instruction is reading register number 3. So here we have a true dependencies because the second instruction cannot execute until the first instruction completes, because the second instruction needs the value that we will be writing by instruction number 1. There is also anti-dependency. It's a write after a read. The first instruction is reading register 1, and the second instruction is writing to register number 1. We don't have a true dependency here. The problem that we have here is that we don't have enough register in our architecture, because if there is enough register, we can change the register number 1 at instruction number 2 with register number 16, and the semantics of the program will still be preserved. And the last one is output dependencies. It's a write after a write. The first instruction is writing to register number 3. And the second instruction is reading register number 3. So here we have a true dependency. But the third instruction is writing to register number 3. So there is no a true dependency between instruction number 3 and instruction number 1. The problem is that we don't have enough registers in our architecture, because if there is enough registers, we can replace the register number 3 at the instruction number 3 with register number 13, and the semantics of the program will still be preserved. Anti and output dependencies exist due to limited number of architectural registers. They are dependencies on a name, not a value. Now, let's see how data dependencies stalls a pipeline. At cycle 0, we fetch instruction A. At cycle 1, we move instruction A from the fetch stage to the decode stage, and we fetch instruction J. At cycle 2, we move instruction A to the execute or ALU stage, and we move the instruction J to the decode stage. At cycle 3, we move the instruction A to the memory stage, but we cannot move the instruction J to the ALU or execute stage because the instruction J depends on instruction A. So we need to wait. And the way that we wait in a pipeline is by adding no ops. So after 3 cycles, the instruction J can execute because the instruction A completed. Well, but that's not good, right? Our pipeline stalls, right? And it affects performance. And we are also not making use of the available resources that we have in our pipeline, because the goal of a pipeline processor was to make use of idle resources. But because data dependencies stalls the pipeline, it means there is time in our pipeline where the resources are idle. So this is not good because this affects performance. So can we do better? An idea is to use an in-order pipeline. In an in-order pipeline, first we fetch an instruction. After fetching the instruction, we move the instruction to the decode stage. At decode stage, we use a buffer called Reorder Buffer to perform register renaming. You don't need to understand that right now. Going forward, it will be clear. And you just need to believe me that by performing register renaming using that buffer, we can eliminate anti and output dependencies. Also, at decode stage, the operand of an instruction can come from the register file or from the reorder buffer. Now, in the execute stage, instruction can complete out of order. Why? Instruction can complete out of order because now we have multiple function units that have different latencies and can execute instruction at the same time. For example, the integer addition takes 1 cycle to complete 1 instruction, and the integer multiplication takes 4 cycles, and the floating point multiplication takes 8 cycles. And because of that, these functional units can update the architectural state out of order. So here what we have is an in-order dispatch or execution and an out-of-order retirement. But this is a problem. Why? This is a problem because the instruction can take different number of cycles in the execute stage. The first instruction takes 11 cycles to complete, and the second instruction takes 4 cycles to complete. After 4 cycles, the instruction number 2 can update the architectural state before the instruction number 1 completes. The problem is, what if the instruction number 1 throws an exception after 7 cycles? This is a problem. Why? This is a problem because the programmer expects that when an instruction throws an exception, all the instructions after that instruction should not be executed. But in this case, in the case of this pipeline, it's possible, right? Because after 4 cycles, the second instruction can update the architecture state. And the question is, can we do better? An idea is to use in-order pipeline with the reorder buffer. In an in-order pipeline with the reorder buffer, first we fetch an instruction. After fetching the instruction, we move the instruction to the decode stage. At decode stage, we use the reorder buffer to perform register renaming. But now we are also using this buffer to allocate an entry for the instruction at decode stage. In that way, we will provide precise exception. Going forward, it will be clear. And after that, again, we can get the operands of the instruction from the register file or from the reorder buffer. And when the operands are ready, we can dispatch the instruction into one functional unit. Again, here instruction can complete out of order, but what is different in this pipeline now is that the instruction update the reorder buffer instead of update the architectural state directly. And the reorder buffer will ensure that the architectural state is updated in the order specified by the program. Before an instruction exits the reorder buffer, we check for exception. If none, we write the result to the architectural state. It can be the register or memory. But if there is an exception, we flush the pipeline and we start from the exception handler. What we have here is an in-order dispatch or execution, an out-of-order completion, and an in-order retirement. So here we have the question, why do we want precise exception? We want precise exception because it hides software debugging. And this also enables easy recovery for exception and so on. So now let's understand how the reorder buffer is helping to solve the problem of updating the architectural state out of order. So the idea is to complete instructions out of order, but reorder them before making results visible to the architectural state. When an instruction is decoded, it reserves the next sequential entry into the reorder buffer. And when an instruction completes out of order, it writes the result in the reorder buffer entry. And when instruction is the oldest in the reorder buffer, and it's as completed without exception, we can move the result to the register file or to memory. That is how we provide precise exception. And here we have a picture of the pipeline now with the presence of the reorder buffer. So now let's understand how the reorder buffer works. We use the reorder buffer to achieve 2 goals. First, to perform register renaming so that we can eliminate anti and output dependencies. And second is to provide precise exception. Now let's see how we can achieve both of these goals by using the reorder buffer. When an instruction arrives at decode stage, first we allocate an entry of that instruction into the reorder buffer. And this entry becomes the youngest in the reorder buffer. It's knowing that this instruction is going to change register number 3. So we go to the register file and we set the valid bit of the register number 3 to 0. And we also write the address of the reorder buffer entry of that instruction into the register file, so that the next instruction knows where to find the register number 3 into the reorder buffer. After that, we go after the operands of that instruction. First, we go after the register number 4, and we look at the valid bit of register number 4, and we see that is 1, so it means we can take the value from the register file. And the same thing happens with the register number 5. When the second instruction arrives at decode stage, we allocate an entry of that instruction into the reorder buffer, and this instruction becomes the youngest. It's knowing that this instruction is going to change the register number 2, so we go into the register file and we set the valid bit of the register number 2 to 0. And we also write the address of the reorder buffer entry of that instruction into the register file. After that, we go after the operands of that instruction. First, we go after the register number 3. We go into the register file, and we see that the valid bit of the register number 3 is 0. It means that the value is not a register file. We need to go to the reorder buffer in order to take the value. So we take the tag, and we use that to access the reorder buffer. When we are at the reorder buffer, again, we check the valid bit of the register of the youngest entry of the register number 3 in the reorder buffer to see if the value is here, if the value is ready. In this case, the value is 0. It means that the value is not ready. So this instruction needs to wait until the producer of this value updates the reorder buffer. And the same thing we do with the register number 1. We go to the register file, and we see that the valid bit of register number 1 is 0. So we take the tag to access the reorder buffer, in this case in the entry number 2, and we see that the valid bit is 1, so it means the value is valid and is ready, so we can take the value of the register number 1. But this instruction needs to wait because the register number 3 is not ready yet. When the third instruction arrives, we do the same thing. We allocate an entry for that instruction into the reorder buffer, and this entry becomes the youngest instruction. And it's knowing that this instruction is going to change or update the register number 3. So we go to the register file, and we invalidate, we set the valid bit of the register number 3 to 0. And we also write the address of the reorder buffer entry of that instruction into the register file. After that, we go after the operands of that instruction. So in this case, both of the operands are valid, so we can take the values from the register file. What is important to note here is that we are in the presence of the output dependency. The first instruction is writing to register number 3. The second instruction is reading register number 3. And the third instruction is writing to register number 3. Without the reorder buffer, the third instruction cannot be executed before the second and the first instruction. Right? Because if the third instruction executes before the first instruction, the second instruction will read the value that was produced by instruction 3 instead of the value that will be produced by the instruction 1. And this affects the semantics of the program. And this is a problem. Now, let's see how, because we are using the reorder buffer to perform register renaming, we can eliminate anti and output dependencies. And here I assume that we are in a data flow processor. Going forward, it will be clear what I mean by a data flow processor. Now, with the presence of the buffer, we eliminate anti and output dependencies because we rename it the register number 3 at instruction number 3 to the entry number 8, and the instruction number 1 was renamed to the entry number 6, and we linked the instruction number 2 to read the entry number 6 instead of the entry number 8. And because of that, we eliminate anti and output dependencies. And the next instruction that will need the value from register number 3, the instruction will take the tag from the register file and knows that the youngest producer of the value of register number 3 can be found at the entry number 8 of the reorder buffer. This is how we eliminate anti and output dependency. Now, let's see how the reorder buffer helps us to provide precise exception. The reorder buffer is a first-in, first-out structure. An instruction can only exit the reorder buffer when the instruction is the oldest in the reorder buffer. That way, when this instruction, number 3, is executed before the second and the first instruction, this instruction we need to wait until the instruction 1 and 2 update the architecture state because they are older than the third instruction. And only after that, the third instruction will be able to exit the reorder buffer and update the architecture state. That's how we provide a precise exception. So here we have another picture of the reorder buffer. We fetch an instruction, and after that, we move that instruction into decode stage. At decode stage, we allocate an entry of that instruction into the reorder buffer in order to provide precise exception. And after that, we perform register renaming to eliminate anti and output dependencies. And after that, we go after the operands of an instruction first at the register file. And if the values is not a register file, we go into the reorder buffer. And if the value is not into the reorder buffer, we can get the value from the bypass path. Now let's see how the bypass path works. So when a functional unit finishes producing a register value, the functional unit broadcasts this register value so that the instruction that depends on the register value can get the operand and then be scheduled to a functional unit. And the functional units, they can complete out of order, but they don't update the architecture state out of order. They update the reorder buffer out of order, and the reorder buffer update the architecture state in the program order specified by the program. So the reorder buffer update the register file and the memory in the program order. Here we can see how the Pentium 3 provides precise exception and also eliminates anti and output dependency by performing register renaming. So here we have the register alias table. That's a structure that holds all the architecture registers. And this register alias table with reorder buffer are used to perform register renaming. And to provide precise exception, they make the register alias table to point to another structure that is called real register file. By using the reorder buffer, we can provide precise exception, and we also can eliminate the anti and output dependencies because this dependency exists because there is not enough register in the instruction set architecture. And the reorder buffer gives us the illusion that there are large number of registers. And that is good. We have eliminated anti and output dependencies, and we also now provide precise exception. But it's not very good because we still have the problem of the flow dependency. So the pipeline is stalled when we have a flow dependency. Truth be told, we cannot eliminate flow dependencies. We can only tolerate flow dependencies. We need to embrace flow dependencies. Now let's see how we can tolerate flow dependencies. So in an inner pipeline, we dispatch instruction. That is the act of sending an instruction to a functional unit. And we also use the reorder buffer to perform register renaming so that we can eliminate anti and output dependencies that are false dependencies. But the problem is that a true data dependency stalls the dispatch of younger instruction into functional units. Let's understand this problem. So first, we fetch the instruction. After that, we move the instruction to the decode stage. At decode stage, we allocate an entry for that instruction into the reorder buffer to provide precise exception. And we also perform register renaming using the buffer to eliminate anti and output dependencies. After that, we access the register file or the reorder buffer to get the values of the operands of that instruction, and we wait until all the operands are ready so that we can schedule or dispatch this instruction into a functional unit. When the instruction is at decode stage, the instruction waits there until all the operands are ready. Only after that, we can move the instruction to a functional unit. And that is the problem. And this example will help us illustrate the problem. So the first instruction is writing to register number 3, and the second instruction is reading register number 3. So here we have a true dependency. So this instruction will be at decode stage until the first instruction is complete, right? Because an instruction can only go to a functional unit when all the operands of this instruction are ready. The problem is that the instruction number 3, number 4, and number 5 are independent instructions. And we have 3 functional units in our pipeline that this instruction can be executed. But because we only have one decode stage, we cannot schedule this instruction to the function units, even though all these instructions are independent. Why? Well, because the second instruction is in the way. We need to wait until the instruction 2 is moved to a functional unit so that we can decode and dispatch the instruction number 3. So that's the problem with our in-order pipeline. The other example is with a load. A load instruction can take hundreds of cycles to complete. So here we have a load instruction that is loading, right, to register number 3, and the second instruction will read the register number 3. So here we also have a true dependency. The problem is that we cannot dispatch instruction number 3, number 4, and number 5, even though we have function units available. Why? Well, because the second instruction is in the way. We cannot move the second instruction to a functional unit until the first instruction completes. So we have a dependency here. It's a true dependency. The add instruction, in this example, stalls the whole pipeline. The add cannot be dispatched because its source registers are unavailable. And later independent instruction cannot get executed. And we also have another important question here. How are the above 2 code portions different? Right? And the answer is that a load latency is variable. It's sunk now until runtime. And the another question is, what does it affect? And then we can think here about a compiler and a microarchitecture. And the question is, can the compiler, for example, reorder this instruction? Or can the compiler also insert no-ops? It's hard for the compiler to do that. Why? Well, it's hard because load instructions have a variable latency, right? For example, at L1 cache, it may be 2 cycles. At L2 cache, it may be 4 cycles. At L3 cache, it can be 8 cycles. And it can take hundreds of cycles if you need to go to memory. So that's why it is hard for the compiler to reorder this instruction or to insert no-ops. And for performance, that is terrible, right? We are stalling the whole pipeline because of one instruction. And the question is, can we do better? In real life, when we have a traffic jam, and this traffic jam is being caused because a car stopped working, what we do, we remove these cars so that the other cars can move. But this same idea we can apply into our pipeline. The problem is similar because in our pipeline, we have an instruction that is stopping all the instructions to move. If we move this instruction, the subsequent instructions that are independent can get executed. So this is the idea of out-of-order execution, also called dynamic instruction scheduling. Now, let's see how dynamic instruction scheduling works. So, dynamic instruction scheduling are implemented as a variation of Thomas Sulu's algorithm. Here, we have the retirement register alias table that we use to update the architecture state. And we have the front-end register alias table that we use to perform register renaming so that we can eliminate anti and output dependencies. And here we have another structure that is called a reservation station. This is the structure that we are going to use to move instruction so that we can solve the problem that we saw in the previous slides, where one instruction was stopping subsequent instruction to get executed. The structure here will help us to solve this problem. Let's see how. When an instruction arrives at decode stage, we allocate an entry for that instruction, and this instruction becomes the youngest entry in the reorder buffer. And it's knowing that this instruction is going to update the register number 2. So we go to the front-end register alias table, and we write the address of the reorder buffer entry of that instruction into the entry of the register number 2. In this way, we are linking the consumer to the producer. After that, we don't wait for all the operands of that instruction at decode stage. What we do now, we move this instruction to a proper reservation station. And this case here, it's an add reservation station. And we can have reservation station for multiplication, division, and so on. After moving the instruction to a reservation station, we go after the operands of that instruction. We no longer get the operands of an instruction at decode stage. We get the operands of an instruction into the reservation station of that instruction. When the instruction is at the reservation station, we go after the operands of that instruction in the front-end register alias table. So first, we go after the register number 3, and we find that the register number 3 needs to be found at the entry number 7 in the reorder buffer. And we use the tag to access the reorder buffer. In this case, is the entry number 7. And we check the validity bit of the youngest entry of the register number 3 in the reorder buffer. In this case, the validity bit is 0. It means that the value is not ready yet. So for register number 3, at the reservation station, we have the tag indicating where to get that value in the reorder buffer, and we also have the validity bit. In this case, we write 0 because in the reorder buffer, the value is not present. And we do the same with register number 1. We access the front-end register alias table, and we get the tag of the register number 1 to access the reorder buffer. So in this case, is the entry number 2. And we check the validity bit of the youngest entry of the register number 1, and in this case is 1. It means that the value is present or the value is ready. And at the reservation station, we update the validity bit of the register number 1 to 1. In that way, we know that the value is ready. But we cannot send this instruction to a functional unit because one of the operands is not ready. And when an instruction finishes, and when an instruction completes, the instruction broadcasts the tag and the value to Reorder Buffer, and the Reorder Buffer will update the entry of that instruction in the Reorder Buffer. In this case, we will update the entry of the register number 3, and we also broadcast the tag into the reservation station so that the entries in the reservation station that are waiting for this operand can wake up and execute. So that's what happens here. This instruction, the multiplication, broadcasts the value and the tag into Reorder Buffer so that the Reorder Buffer updates the entry, and also broadcast the reservation station so that this instruction can wake up, and when the valid bit of all the operands of an instruction are ready, the instruction uses the tag to access the Reorder Buffer to get the values, and then we can dispatch the instruction into a functional unit. To update the architecture state, we use the retirement register alias table. When an entry becomes the oldest entry in the Reorder Buffer, we just point to that entry. So in this case, when this entry here becomes the oldest entry in the Reorder Buffer, the entry of the register number 3 in the retirement register alias table will point to this entry. So this is how we update the architecture state. Here we have another illustration of an out-of-order machine with precise exception. First, we fetch an instruction. After fetching the instruction, we move the instruction at decode stage. At decode stage, we allocate an entry for that instruction into the Reorder Buffer to provide precise exception. And we also perform register renaming using that buffer to eliminate anti and output dependencies. And we move the instruction to a reservation station to tolerate latencies. And when the instruction is at the reservation station, the instruction goes after the operands. And when the operands of the instructions are ready, the instruction can get scheduled. We can dispatch the instruction. And when a functional unit finishes computation, it broadcasts the value into the reservation stations so that if there is a reservation station that depends on this value, this reservation station can wake up, and after that, we can dispatch this instruction into a functional unit. So here, we move instruction into reservation station in order, we execute out of order, and we update the architecture state in order. So in the hump number 1, we have the reservation station, also called the scheduling window. At the hump number 2, we have the reorder buffer, aka the instruction window or active window. Here is an example in a modern processor. Here we have the front-end register alias table that are used to perform register renaming, and we have the retirement register alias table that are used to update the architecture state in the program order. The problem with the in-order pipeline is that it provides an in-order dispatch or scheduling, and to solve that problem, we need an out-of-order dispatch that we just saw in the previous example. And the benefit of an out-of-order dispatch or scheduling is that we can tolerate latency. It allows independent instruction to execute and complete in the presence of a long latency operation. So here I have this example. I have the first instruction that is a variable A that we hold the result of the computation of the variable x plus y. And the second instruction, we have the variable B that we hold the value of the computation y divided by 10. And we have in the third instruction, the variable C that we hold the result of the multiplication of the A and B. So now let's see how out-of-order machines work. So we transform these operations into nodes. And this node here, to get executed, we need the two operands to be ready. So in this case, we need the x and y operands to be ready in order to execute this node. That is an addition. The problem is that these operands are memory operands, right? And this takes time to get the value of these operands. For the addition nodes to get executed, we need both the x and y to be ready. But for the division, we need the y and 10 to be ready. So when if the y operand is ready, and because here we have a constant, and the constant is fast to get, well, this node division can execute. So this is the node division will execute fast than the node addition. Why? Well, because the operands of the node divisions are ready. And a data flow machine, an instruction to be executed, the only requirement is for the operands to be ready. So that's why this instruction, the division node, will execute fast than the addition. And this fact contradicts the program order. To enable out-of-order execution, we need to link the consumer of a value to the producer. And we do that by using register renaming. We associate a tag with each data value. And we need to buffer instruction until they are ready to execute. We insert instruction into reservoir station after renaming. Instructions need to keep track of readiness of source values. And we do that by broadcasting the tag when the value is produced. And the instruction compares the source tags to the broadcast tag. And if it's a match, the source value becomes ready. And when all source values of an instruction are ready, we need to dispatch the instruction into each functional unit. An instruction wakes up if all sources are ready. If multiple instructions are awake, we need to select one per functional unit. Here, we have an example of an in-order and an out-of-order dispatch. The in-order dispatch with precise exception takes 16 cycles to complete the execution of all these instructions, while the out-of-order dispatch with precise exception takes only 12 cycles to complete all these instructions. And in the real world, the performance gain of the out-of-order dispatch is higher than we can see in this example. And this is my mental model of an out-of-order machine. Now, we are happy because we can tolerate data flow dependencies. Now, let's talk about handling out-of-order execution of loads and stores and how it influences the TCO memory model, right? Until now, we have only covered things about registers, but what really matters to us when we talk about memory models is memory operations, right? So you should consider everything I covered in the previous slides as a background to understand the rest of the talk, because the goal of the talk is really here, right? It's really understanding how the way the modern processors handle out-of-order execution of loads of stores affects the visibility of stores operations. So far, we have considered mainly register as a part of state. But what about memory? Because what really matters when we talk about memory models is memory operations. So what are the fundamental differences between registers and memory? First is that register dependencies are known statically, and memory dependencies are determined dynamically. Register state is small, and memory state is large. And register state is not visible to the other threads or processors, but memory state is shared between threads or processor in a shared memory multiprocessor. Here is really the focus of the talk, because we are going to see how the store queue or the reorder buffer affects the visibility of stores operations and consequently how it affects the TCO memory model. So we need to obey memory dependencies in an out-of-order machine, and we need to do so while providing high performance. The observation and the problem is that memory address is not known until a load or a store executes. When the operands of an instruction are only registers, at decode stage, we can get the ID of these registers because we don't need to compute anything in order to get the ID of registers. And the ID of registers is the only thing that we use to check if there is a dependency or not in instruction that use only registers. The ID of the register is the thing that we use to check for dependencies between instructions that the operands are only registers. But when we're talking about memory operations or instructions in which the operands are memory, well, we need first, right, when you talk about loads and stores, we need first to compute the address of the load or the store, and only after that we can send a request to the DRAM memory, right? We cannot dispatch a store or a load before we compute the address of the store. So that's the difference between registers and the memory operations. So the corollary number one is that renaming memory address is difficult. And the second corollary is that determining dependence or independence of loads or stores has to be handled after their partial execution, as I just described it, right? We need to compute the address first in order to execute a load on a store. And the third corollary is that when a load or a store has its address ready, there may be older or younger stores or loads with unknown address in the machine. The third corollary is also called memory disambiguation problem. So the question is when to schedule a load instruction in an out-of-order engine. The problem is that a younger load can have its address ready before an older store's address is known, also known as the memory disambiguation problem or the unknown address problem. It's important to mention that loads and stores have two different types of latencies. There is the latency of the address calculation, and there is also the latency of writing to memory and reading from memory. And we have this example to help illustrate the memory disambiguation problem. So here we have two instructions. We have a store, and to compute the address of the stores takes 100 cycles. Again, before we send a store request, we need to compute the address. And to compute the address of the stores takes 100 cycles. And we also have a subsequent load. And also, before we send a load request, we need to compute the address. And the computation of the address of this load takes 2 cycles. And the question is this load dependent on that store, right? And how do we check if a load is dependent on a previous store? The thing that we use to check the dependence of memory operations is address. But here, address have different latencies. For example, the stores take 100 cycles, and the loads take 2 cycles. After 2 cycles, the address of the load instruction is ready, and we can send a request to memory. But we don't know if this load is dependent on these previous stores, because the address of these stores is not ready yet. Why? Well, because it takes 100 cycles. So that's the problem. Because if we send the load request, it may load the wrong value, because this load may be dependent on these stores. That's the memory disambiguation problem. When the address of a younger store is ready, but the address of previous stores is not ready. So here we have another example, and this example will help us illustrate that the problem is bigger. Here we have a store that the computation of the address takes 900 cycles. And then we have a subsequent store that the computation of the address takes 500 cycles. And after that, we have a subsequent load that the computation of the address takes 2 cycles. What's important to mention here is that the load instruction is going to load 4 bytes. And that means that this load request is going to access 4 different memory locations. And what makes the problem more complex is the fact that the first store maybe is writing to the last location of the 4 locations that this load is going to access. And the second store maybe will write to the second location of the 4 locations that this load is going to access. That means that for a very location that a load is going to access, we need to check if there is no previous store that's going to write to this location. And this is possible because modern computer architecture gives us the possibility to address a memory in different granularities. We can access memory at the granularity of 1 byte, 2 bytes, 4 bytes, or 8 bytes in x86, for example. A load's dependency status is not known until our previous store address are available. So we have some questions here. How does the out-of-order engine detect the dependence of a load instruction on a previous stores? We have 2 options. The first option is to wait until all previous stores committed and there is no need to check for address match. The option 1 is not good for performance. Why? Well, because we need to wait until all previous stores have completed. For example, if we have 15 stores, we need to wait until all these 15 stores complete so that we can dispatch the load instruction. But this is not good. Why? Because maybe the load is not depending on the previous stores. And the second option is to keep a list of pending stores in a store buffer and check whether a load address matches a previous store. So this is a better option. And going forward, we will see why. So the next question is, how does the out-of-order engine treat the scheduling of a load instruction with regards to previous stores? So here we have 3 approaches. We have the conservative approach, is to stall the load until all previous stores have computed their address or even retired from the machine. So here, we wait until all previous stores have completed so that we can dispatch a load instruction. And that's not good for performance. Think about a program in which all loads are independent because these are shared variables that were writing by another processor. And the second approach is the aggressive approach. Here, we assume the load is independent of unknown address stores, and we schedule the load right away. But later, we need to check if the prediction is right or wrong. And if it's wrong, we need to execute the load again. And the last approach is the intelligent approach, is to predict. The intelligent approach is similar to the aggressive approach, but the difference is that now we are adding a sophisticated hardware inside of the pipeline that we make prediction based on the behavior of the program. And here we also need to check if the prediction that was made is right or wrong. And if the prediction is wrong, we need to execute the load again. And here we can see that the perfect approach or the intelligent approach have better performance. And predicting store load dependencies is important for performance. Now let's talk about data forwarding between stores and loads. We cannot update memory out of the program order, and we need to buffer all the stores and load instruction in instruction windows. But even if we know our address of path stores, when we generate the address of a load, 2 questions still remain. The first, how do we check whether or not if a load is dependent on a store? And the second is, how do we forward the data to the load if it's dependent on a store? So there are two important questions. Modern hardware use a load queue and a store queue for this. And we can combine or separate between loads and stores. A load search the store queue after it computes its address. Why? Because here we assume that when a store finishes the computation of its address, it writes the address in a store queue. And a load search this queue to see if there is an address that matches with its address. And if there is a match, it means that this load is dependent on a previous store. A store searches the load queue after it computes its address. Why? Here we are assuming that we are using the predict approach, because here we are using prediction. And if we predict that a load is not dependent on a previous store, we need to check somehow if the prediction is right or wrong. And to be able to perform the prediction, we have a buffer in which when a load finishes the computation of its address, the load writes its address in that buffer so that when a previous store finishes the computation of its address, the store can search the load queue to see if there is a load that was already dispatched that depends on the store. And we do that by checking addresses. Now, let's talk about out-of-order completion of memory operations. When a store instruction finishes execution, it writes its address and data in its reorder buffer entry or store queue entry. And when a later load instruction generates its address, it searches the store queue with its address. Or if the value is not at the store queue, we need to access the memory, again with its address, and we receive the value for the youngest order instruction that go to that address, either from the reorder buffer or memory. This is a complicated search logic implemented as a content addressable memory. Content is memory address, but also includes the size and the age. This is also called store-to-load forwarding logic. When we talked about register renaming, we didn't use content addressable to search the reorder buffer. We used it in direction. So why we need to use content addressable memory to search the store queue? We need to use content addressable memory in the case of stores and loads because memory state is large and register state is small. And because the register alias table is small, we can use indirection to access the reorder buffer. But we cannot do that with memory. Why? Because we use 48-bit memory address that can directly address every byte of 256 terabytes of storage, which means to use indirection to access the reorder buffer, we will need a structure with 256 terabytes of entries. And we can't have it in a pipeline. Here we saw that this is a complicated search. And here we are going to see how complicated it is. It's complicated because a content addressable search, right? We cannot use indirection because memory state is large. It's also range search. It's based on address and size of both the load and the only store. It's age-based search because we need to get the youngest value that was writing to that particular address. And the load data can come from a combination of multiple places. One or more stores can be in the store buffer, and others can be in memory. For example, in the case of the load that was going to access 4 bytes, for example, that means that the load is going to access 4 locations. We can find 3 locations in the store queue, but one of the locations is not in the store queue. We need to go to memory. Here, we have an example of the complexity of searching the store buffer, but I'm not using all the components or elements that should be a part of the search. I am only illustrating the content addressable search. So when the address of a load is ready, we search for every entry of the reorder buffer to check if there is a match. And this can take a lot of cycles to complete. And if there is no match, we need to go to memory. And when going to memory, we can miss in all the level of the memory hierarchy because because maybe the value is not at L1, it's not at L2 or L3, it's not even at DRAM. We need to go to the disk. It's not good because when the address of the load do not match at the store queue, it's a lot of overhead because we need to search the queue, and after that, we need to go to memory. So now we are going to see how the reorder buffer affects the total store memory model. And for that, I have an example. When a store arrives, we allocate an entry for that store in the reorder buffer. And this entry becomes the youngest in the reorder buffer. To compute the address of this store, take 100 cycles. And the value that we'll be writing in that location or address is not ready. Why? Well, because it's being produced by another instruction that takes a lot of time to complete. Because the address is not ready, and the value is also not ready, we update the reorder buffer entry of this instruction by setting the address bit to 0 and the valid bit to 0. Because the value and the address are not ready. After that, the second instruction arrives, and we also allocate an entry for that instruction in the reorder buffer. And this entry becomes the youngest. And to compute the address of this store only takes 2 cycles. And the value that we'll be writing in that address is ready, right? It was already produced by another instruction that already completed. So the value is ready. And we update the reorder buffer entry of this instruction by setting the address bit to 1 and the value bit to 1, because both the address and the value are ready. And the value in this case is 25. But it's important to understand that even though the second instruction completes before the first instruction, the second instruction cannot update the architecture state before the first instruction. Why? Well, because the reorder buffer is a first in, first out structure. An instruction can only update the architecture state when it becomes the oldest instruction in the reorder buffer. That's why the second instruction cannot update the architecture state before the first instruction. And the question is, how is this behavior influencing the total store memory model? The influence that this behavior is causing in the total store memory model is that there is no need for fences between stores and stores. Why? Because the reorder buffer is a first in, first out structure. An instruction can only update the architecture state when it becomes the oldest instruction. The reorder buffer gives us the guarantee that a subsequent in-program order store will not update the architecture state before the previous store. This is how this buffer influences the total store memory model. So now let's understand how the reorder buffer affects the visibility of stores operations. So when a subsequent load in the same program tries to access the same location that was already written by the second store, this load can take the value from the reorder buffer. And in this case, this load will take 25 from the reorder buffer. But if a different thread from a different core try to access the same memory location, right? A load in another thread that is in different core tries to access the same address, this thread will load the wrong value. Will load the different value. Why? Well, that thread that is from different core do not have access to this buffer because this buffer is local to this thread. So that thread, we need to send a request to the memory controller to get the value from the memory. And that's how two threads or processors in the system can have different views on how memory operations took place. And we also use this buffer because sometimes in our pipeline, we have the address of the store ready, but we don't have the coherence permission to modify the cache block, right? And then instead of stall the pipeline until we can have the coherence permission of modifying the block, we write to a buffer. And we also use this buffer to update the main memory in the program order specified by the program. Because instead of updating the memory directly, we are writing to this buffer so that we can handle execution of loads and stores out of order. And this also helps with performance, because now when it's a match, when a load match here, we don't need to go to memory. Right? We can get the value directly here from the buffer. And this reduces the latencies of loads. So now I hope this example is clear, why we write to buffer, why this buffer exists, and why it is important. I hope now you can understand, right, that this buffer is not only here because computer architects think that they should be here. They are here because they are important, and we saw why it is important. Modern processors today have more than one thread inside of a core. And here we are going to see how hyperthreading interacts with the total store memory model. So here we have an example. We have global variables. We have x, we have y, and we have p. And we have a core. And inside of this core, we have two threads because we are talking about hyperthreading. So the second thread writes to x and allocate an entry in the reorder buffer, and this entry becomes the youngest. After that, the first thread also updates the variable x in the reorder buffer and now allocates another entry and now becomes the youngest in the reorder buffer. After that, the second thread needs to load the value of x to compute p plus x. And the question is, which entry of x in the reorder buffer, because here we are using, this is one core with two threads, and we only have one reorder buffer, right? We only have one reorder buffer. And the question is, from which entry in the reorder buffer the second thread needs to get the value of x? Should the thread get the value of x from the youngest entry in the reorder buffer that was written by the thread number 1, or should the second thread get the value of x in the entry that the thread number 2 allocated? In other words, what's the value of p? Should the value of p be 10 or 300? So in the TCO memory model, the thread number 2 needs to get the value from the entry that was allocated by the thread number 2. And in this case, the value of p needs to be 10. And how it's implemented? It can be implemented in two ways. We can have, for each thread inside of a core, its own buffer, Or we can add an additional column in the reorder buffer that we need to access while we are searching in order to find the value that a particular thread brought, and not the entry that was allocated by another thread. Now we are going to see all the reasons why modern computer architectures perform out-of-order execution. First is memory. As you can see in this picture, most of the time, the processor is idle, waiting for data to come from memory. The other reason is that memory latency is almost constant. The other reason why we have out-of-order processor or restricted data flow processor is to exploit memory-level parallelism. Let's understand what I mean by that by using this example. So we have a thread A is computing. After that, the thread sent 2 requests to DRAM. It's important to mention that when the requests are going to different banks, they can be served in parallel. But if the requests are going to the same DRAM bank, they will be served in serial. But in this case, the 2 requests that the thread sent are going to different banks. So that's why this request will be served in parallel. So the first request is sent to memory, to bank 0. After that, the second request is also sent to memory, to bank 1. And because of that, we can process this request in parallel. And after some time, the first request completes. And after some time, the second request is also complete. And after that, the thread can start computing again. So bank access latencies of the 2 requests overlapped, and the thread stalls for 1 bank access latency. It's the memory. It is a quote from Richard Seiters that implemented the fastest processor of its time. And this processor was designed to complete 4 operations in 1 cycle. But because of memory latencies, the processor was completing 1 operation in a very 4.5 cycles. So that's why he said that's why he quoted this. Thank you very much for attending my talk. This is the end of my talk. I hope you found something interesting here. See you next time.